In this lesson, we're going to be talking about the basics of electrical circuits. Now, electrical circuits are going to be across all parts of this trade. Everything you do as a service technician, most of what you do as an installation technician, is going to involve some sort of electrical circuits or not. So this is probably pretty important information. Okay, we start off with direct current when we talk about electricity. Okay, direct current is current that travels in one direction. Negatively charged particles flow through to atoms with positive charges. Okay, because remember, the atom is our most basic part of matter. Current flows from a negative to a positive. So electrical circuits powered by batteries are direct current systems. The electrical symbol for a battery is found down here at the bottom of this slide. Okay, and it's probably one pretty important to remember because if you see this on a diagram, you're dealing with a DC or direct current circuit. Alternating current is our most commonly used power point or our power source in HVAC. Okay, electron flow continuously changes direction. In other words, there is not a single true positive and not a single true negative. It's more economical to produce and deliver than a direct current. And the electrical symbol for alternating current is the circle with the sine wave or squiggly line inside of it. Okay, in every circuit, we have certain parts that have to be there. We have a power source, we have a load, we have a switch, and we have conductors. Okay, the power source is what provides source for the source voltage for the circuit. Power source could be alternating current or direct current. It really doesn't matter in terms of parts of a circuit. We have to have a load. It's a device that uses electrical power. It could be a motor, light. It could be a resistive load like a light bulb or a heater, and it could be an inductive load that creates magnetism like a motor. We have to have a switch, some sort of control that turns it on or off. We have to have conductors that provide a path for the current to flow. It's the wiring. Could also be a printed circuit board. So without any one of these four parts, the circuit will not work and behave properly. Okay. Here's two examples of an electrical circuit. We have one where the light bulb is on down at the bottom and the second where the light bulb is off up top. Okay, you notice we have the source. That's our hot and neutral. We have our switch. In the top circuit, the switch is open. Therefore, there is not a flow of current going to the bulb. In the bottom circuit, the switch is closed. The switch passes power. And the device, the load, which is a light bulb in this case, is functional. Okay, so again, we're introducing two terms here that we have to be very important on. Closed switch passes power. Open switch doesn't pass power. So in this circuit, it's a slightly different variation of the one I showed you on the last slide. The switch passes power when it's closed. The fuse passes power until it burns out and opens. And the thermostat is set to pass power to the light bulb when the temperature drops below 35 degrees. We have units of measurement in electricity because we have to be able to quantify our electrical power and our electrical circuits. The first unit of measure is voltage. It's called electrical pressure or electromotive force, EMF. It's measured in volts, and in our Ohm's law calculations, which we'll start to talk about, it's indicated by an E. Then we have current. Okay, current measures the amount of electron flow per unit of time. It's the speed of the current flow. It's how fast the electrons are moving. It's measured in amps, and it's usually indicated by an I in Ohm's law. Resistance is the opposition to electron flow, okay? Every load has resistance. It actually, as it uses work, as it uses electricity, it provides the resistance and controls the flow of current. Okay, it's measured in ohms, and in Ohm's law, it's calculated by R, or indicated by R. Okay, we can mathematically prove the relationship between voltage, current, and resistance by the use of Ohm's law. Okay, Ohm's law is simple. When you look at it, it takes 1 volt of electrical pressure to push 1 amp of current through 1 ohm of resistance. For most electrical circuits, the same A circuit with a low resistance will have a higher current than a circuit with a higher resistance. The resistance is what provides the control for electrical flow. So when the calculations for Ohm's law, when put out into an equation, say current equals voltage divided by resistance. Voltage is current times resistance. Or resistance is voltage times current, or voltage divided by current. Power is voltage times amperage. These calculations only work with purely resistive circuits, but the principles of it apply to most circuits we use in HVAC. The numbers may be a little bit different when we're talking about circuits that have magnets in it, for example, motors and things like that, inductive circuits. So the easiest way to deal with this is you map out a circle, okay, E over I times R. So to find voltage, cover the E, it's I times R, so current times resistance. To find current, cover the I, it's E divided by R, which is voltage divided by resistance. To find resistance, cover the R, and that leaves you with E over I, or voltage divided by current. There's additional tables and stuff in your course materials. You can find all sorts of different formulas and different ways to calculate Ohm's law. We want to take measurements, okay? Voltage readings are taken across loads, switches, and sources of power. Amperage readings are often taken with a meter that clamps around a conductor. Resistance readings are taken on circuits that are de-energized and with the component being checked and isolated from the circuit. We have a few different types of circuits as well that we have to talk about. Okay, a series circuit has only one path for electricity to flow. Okay, one path. Current is the same at all points in the circuit. The total resistance of a series circuit is the sum of all resistances in the circuit. Voltage is divided between all loads in the circuit, and a break or an open anywhere in the circuit will stop the electron flow through the entire circuit. Okay, so this is an example of a simple series circuit. We have a battery, we have some wires, which is our path, we have a switch, and we have a load. Okay, now, again, any open in the circuit will prevent the current from flowing. We have an open switch. Close the switch, the light bulb energizes. Open the switch, the light bulb turns off. Okay, close the switch, the light energizes. So now I have a complete flow of electrons. We have our source, we have our path, which is the wiring, we have the switch, and we have the load. Okay, loads in series are not all that uncommon. Okay, you must know how to troubleshoot. When two or more loads are in series, the amount of voltage used by each load is determined by the resistance of the load and the amperage of the circuit. E equals I times R. The total voltage will equal the sum of the voltage drop at each load. In other words, if I calculate out load 1, load 2, load 3, add them all together, that has to equal my source voltage. Amperage drop in a series circuit is the same at all points in the circuit. Resistance is the sum of all resistances. Okay, this is another type of series circuit. We have a generator, I have a switch. I have 3 heating circuits in series, one path for electricity to flow. So voltage is split through all those elements, and current is the same. Parallel circuits are the opposite. We have more than one path for electrons to flow. The source voltage will be the same at all loads. So I have my source, which is 120 volts, single phase, 60 hertz. This is just another way to designate that. Okay. Then I have a thermostat and a fan motor. Okay. Now, This is a parallel circuit. Notice I have a switch, but every single one of those heaters gets power when that switch closes. So every one of them is getting source voltage. Okay, again, every load, the compressor, the blower motor, and every load in here is getting source voltage. Whatever the voltage is across L1 and L2, in this case it's 240, single phase, 60 hertz. Parallel circuit rules, voltage stays the same at every load, it's source voltage. Amperage adds up with each load added in the circuit. In other words, if we have the compressor has 12 amps, blower motor has 1 amp, and the relay coils C and BR down there each have 0.5 amps. So I have my 12, 1, that's 13, 0.5, 0.5, that's 14 amps when this circuit is all energized. This is the type of circuit that is used in your house. Every light adds to the amperage. Every appliance adds to the total amperage of what you're using. Power adds up. Total resistance is smaller than the smallest individual resistance. Okay, let me say that again. The total resistance of the entire circuit is smaller than the smallest individual resistance in the circuit. To calculate for I, it's determined by each load and resistance. The less resistance a load has, the higher the amp draw will be. The total current flow of the entire circuit, in other words, IT, is all of the currents added together. Current can be calculated with Ohm's law, E equals I times R. Each load uses total voltage supplied, unlike the series circuit. Voltage drop in a parallel circuit is whatever line voltage is. So total voltage is the same. E1 equals E2 equals E3 equals E4. Total resistance will be less than the smallest resistance. Total resistance cannot be obtained by adding all of them together. Okay, you have to use a formula for parallel circuits and resistances. So RT for two resistances in a circuit is R1 times R2 divided by R1 plus R2. Now be careful. Order of operations. You do your multiplication first, okay, then your two addition, and then divide the two numbers. Okay, if you have more than two resistors, to calculate total resistance, you do 1 over R1 plus 1 over R2 plus 1 over R3. Okay, it's called the reciprocal formula. Power is the sum of all wattage. Okay, power is wattage. It's the sum of all wattage readings. Okay, so it's P1 plus P2 plus P3, etc. Power can be calculated with Ohm's law. You need two values. Okay, P equals I times E. So I have to have two values. Okay, so again, basic part of a circuit when we talked about this, okay, you have to have a source, you have to have a path, you have to have a switch, you have to have a load. To recap, we have alternating current and direct current. Direct current is a battery. Okay, alternating current is what's most often used in the field. Okay, it's what's supplied through your plugs and outlets in the house.